Well, thank you very much. I'd also like to add my thanks, of course, to Tom and Terry and the rest of the organising committee for inviting me here. And I'm going to return to the theme of urban flows and link in, I think, with what Martin and Catherine talked about earlier today. I'm really going to talk about natural ventilation of buildings and how that links into this grand challenge about how we build a sustainable city. And as you've already heard, we're all going to be living in cities practically by about 2050, and this creates huge amounts of challenges but opportunities. And as Martin pointed out, a lot of the cities have yet to be built, and we're very interested in fact using timber for building cities instead of concrete, because that way you sequester the carbon, and there's a group of us in Cambridge who work on this problem, and here is an example of a design for a wooden skyscraper in London, which I'm afraid has not got planning approval. But there we go. And of course we all know that climate change is a big issue, and it's expensive. It's estimated that it costs about 1.2 trillion annually the damage, and if you want to put that in context, that's about half the UK GDP, or it'll be double it after Brexit. So the question is, why do we want to build green buildings? Here is an example. These are the million tons of carbon equivalent released over the last 50 years or so. And you can see, to my surprise, that buildings outstrip both transportation and industry. On a hot day in Los Angeles, more energy is used in cooling the buildings than in the cars driving around the roads, which I find an amazing result. And it comes about because we build buildings like these, which are essentially greenhouses. They're glass boxes, and they're very efficient at growing greenhouse gases. If you do, which has been done, a survey of people who work in commercial buildings of this type that are fully air-conditioned, you find that most of them think they're horrible. Everybody knows that in a US building in the winter you have to go in and take your clothes off because they're too cold, and in the summer, they're too hot, you have to take your clothes off, and in the summer you have to put clothes on because they're too cold. So we don't even get the sign right. Okay, there's a real concern that this is actually just going to get worse. Here's a recent report from the International Energy Agency saying that energy demand in buildings could increase by 30% by 2060. And in their report on the future of cooling, I've taken a few phrases here from their executive report, which you can read, but I think it's very clear that something needs to be done. And if you look at the energy consumption in space cooling for buildings, you can see it rises inexorably and is going to continue to do so. So it's a serious problem. It's a serious contributor to greenhouse gas emissions and so on. So what can you do about that? And here are the culprits, the air conditioning units. I lived in San Diego for 12 years, and the weather there is absolutely perfect. My neighbor installed one of these on the side of his house and blew all the hot air out of his house directly into my living room. So it meant I had to close the windows in my living room because of that. And that happens citywide. So all over the cities, these kind of things are pumping hot air out that they're extracting from buildings, and they're contributing to the urban heat island and the stresses that we all are aware of. So how do we get rid of these things? Well, one of the things that we're also concerned about is the quality of the external air. We know that there's a lot of emphasis currently on air pollution. In the UK, we exceed our annual limits for air pollution, typically in the first 3 days in January. So it's a really big problem for us, and we're doing a lot of work to try and deal with that. And we know that this has huge health consequences. It costs the UK, we think, around £10 billion a year, which will be our GDP by the time we leave Europe, and is a very major contributor to health and deaths worldwide. as a result of this, we actually have a project which is called a Grand Challenge project, which is called MAGIC, stands for Managing Air for Green Inner Cities. For this, in order to get this grant, we had to come up with a Man on the Moon mission statement. And so our Man on the Moon mission statement is the 0-0 Grand Challenge, which is that we will develop cities with no air pollution and no heat island effect by 2050. And I'm aware that that's unlikely. But the point is it's meant to give a direction for decisions. So if you're making a decision which makes air pollution worse and increases the heat island effect, it's probably the wrong decision to make. Okay, and I'll tell you more about MAGIC as we go along. But what we're imagining then is a city with no air pollution or heat island. We need to think differently about cities. I've showed you these glass boxes, so we're interested in maybe we can make buildings much more porous. We can use natural ventilation to cool them rather than air conditioning. And we're also very interested in integrating green and blue spaces. Martin talked about green roofs and so forth. And of course, eventually we want to change the way we behave. And we know that green spaces and blue spaces are cooler. I think this is the same map that Martin showed, but here is Richmond Park, which is a big park. And on this hot day in summer, the ground temperature is 23 degrees. In the west end of London, it's 31. And you can see by this blue region that the Thames is relatively cool. So how much can you build on that also to make places more habitable? So it all started back in the beginning of the 20th century when air conditioning was invented by Carrier and was first introduced into a building in the very early part of the 20th century in Buffalo in upstate New York, so-called Larkin building, and it was designed by Frank Lloyd Wright. And what I think is notable about this building is it looks nothing like any of the nice buildings that Frank Lloyd Wright designed. And rightly so, this no longer exists, whereas all of his other ones do and are cherished. And the other thing to note about this building is that it doesn't look anything like a modern air-conditioned building. It looks like a traditional building, lots of thermal mass, thick walls, small windows, and the result of air conditioning has changed the way we build buildings completely, but with the energy consequences that I outlined before. And what's the problem? So, my thing is falling off. Just don't mess my hair up. Okay, so let me try and explain the problem. Suppose you're in a totally insulated room on your own. You give off about 100 watts. You're like a rather bright light bulb. And you need about 10 liters per second of air to breathe so that the carbon dioxide doesn't build up too much in here and feel stuffy. If this is a totally insulated box that's built by no builder I've ever met, but where everything is sealed, then this airflow will raise the temperature just by this 100 watts by 10 degrees C. So if it's 10 degrees outside, it's 20 degrees inside, and you're fine. So the heating problem is not a really big energy problem as long as you insulate well. You just need to, if it gets down to 0, you add another light bulb, and you're fine. Okay, Eckhart.
I'm trying to make sense of the 10 liters a second.
Yeah, it's no, but you don't want carbon dioxide levels to build up, so you need to refresh, and you breathe out a lot of, you don't breathe it in and out, but that's the flow rate you need basically to keep the whole thing going. Yeah. Okay. On the other hand, if you cool, everything is the same, of course, and now this 10-degree difference means that if it's 25 outside, it's 35 inside. So that's the fluid mechanical problem. If you want to make this 25 or 26 degrees, you've got to increase this flow rate by a factor of 10. And that's a ventilation problem. That's a fluid mechanical problem. So I'm interested in that problem, right? And so that's the question: how can you generate big airflows in situations where you're just using natural forces, natural ventilation? You're not providing any cooling, and you're not using any mechanical ventilation. So that's the challenge, essentially. So this is the fluid mechanics problem, and I think it's nice to compare and contrast two things. if you think about flows around aerofoils, for example, the only thing that really matters here is the geometry of the aerofoil and the angle of attack. You don't care much about the properties of the fluid, whether its density changes or anything like that. On the other hand, so the whole flow is governed by the boundary conditions here. And if you go to something like a hurricane, then it's all determined by the internal dynamics, the release of latent heat and the convection, and you don't care about the boundary conditions that much. You don't care about the shape of the domain, for example, very much. Okay? And in buildings, that's exactly, both of these things matter hugely. So buildings, I think, are more difficult than rocket science, and in fact, meteorology and oceanography, just to be provocative. Okay, so let me show you how boundary conditions matter. Right, so here is a hot building, and all I've done is open an opening here and an opening there, and this one. And on this building, I've closed this opening and opened the same size opening down here, right? And the flow is completely different, as you can see. You can see that in this case, the cold air falling down keeps this relatively well mixed. This is called mixing ventilation. And in this case, the cold air coming in here stays underneath this warm layer and just pushes it out through this displacement ventilation. So all you've got to do is change the position of the opening, and everything is completely different. Okay? So depending on whether this door is open and another window is open up there, things will be different depending on how you arrange that. And that's hard to deal with. And then the internal dynamics are interesting. As I said, you all give off 100 watts. So above all of you is a plume rising, as you can see here, turbulent flow. We all know lots to know about plumes. We've heard a lot about them this week. We know they entrain. Here's an example of two plumes rising and merging because they entrain air from between them. We know their volume flux increases with height and that the temperature decreases with height. So we know a lot about these things, mainly due to my PhD supervisor, Stuart Turner. But we have to deal with this as well inside a building. So we're going to use natural ventilation because it's free. And there are two sorts. So there's the wind, obviously, and then there's the heat. Solar gains, sun shining on the building, or internal gains, as I said already, people, computers, machinery, whatever. And how are we going to use these in order to ventilate our buildings? Okay. There's also, as Catherine said, increasing evidence that natural ventilation improves productivity. It's kind of hard to know for sure, actually. But there's been some recent measurements that suggest that it actually increases brain activity when you're subject to something where the environment changes in time compared to something where it's static. So I think this is an interesting development and may provide some basis for this idea of increasing productivity. And in terms of a building owner, if you can get 5% more effort out of your workforce, it outweighs every other economical consideration, pretty much. And we can build these buildings that work well. This is a building built by Alan Short and others. He's now the Professor of Architecture in Cambridge, won the Green Building of the Year in 1995. And I worked on the airflow model of this building. So for 20 years, we know how to build buildings that are very efficient, very effective, produce wonderful internal conditions. And you can see this looks a lot more like the Larkin building than many other modern buildings. Has some interesting features like this tall stacks here. And I'll try and explain how that all works. Okay, so as I said, we have natural ventilation, we have wind-driven ventilation, and temperature-driven ventilation, which in the jargon we all call stack-driven. And I showed you an example of displacement and mixing, and we will talk later about cross-ventilation, the single-sided wind-driven ventilation. And then at the end, we'll combine them together and see how they interact. Okay, so this is stack-driven displacement ventilation. This is imagining that we have a single heat source in a space. The hot air leaves at the top and there's cold air coming in below. And you set up this stable density interface here. And so what happens is the fluid that comes in through the bottom, the air that comes in through the bottom, is entrained into the plume, carried across to the upper layer, and leaves. It's a very simple case. It's as column spherical cow example, but we can analyze it. So what happens here, as I've just said, is the air comes in with some flow rate Q. It crosses the interface in the plume, so that Q and that Q must be the same, and it leaves with the same flow rate because the volume is fixed in a steady state here. And if you take the heat balance for this upper layer, then the heat coming in, which is actually the heat flux in the plume, that excess temperature here must be the same as the excess temperature here, because the heat must leave at the same rate if it's in steady state. And so this has just a single temperature, so it's a very easy thing. And what you want to do is to arrange things, in particular the size of these openings, to make sure that this plume, this hot region, is above your head. Okay. I don't know where it is in this room, but when I sat up at the back, Ed Llewellyn said it's where all the cool people sit. And I can assure you that that's completely wrong. It's where all the hot people are sitting. Right. Okay, so what happens is that now we have this plume, and we know if we have a certain heat flux, we know what the volume flux is because we know about plume theory. It scales with the heat flux and the distance from here to here. And we know the temperature difference as well, which scales in this way. Okay. All right. And so you can calculate the flow through this. You just imagine this upper layer. There's a pressure difference across here and a pressure difference across there, which are given here. I'm not going to do the analysis. You can calculate the flow rate as a function of this combination of upper and lower areas, and effectively the buoyancy of this upper layer here. And I want to just discuss this equation a bit. Right? So suppose that the upper opening is very small compared to the lower opening. All right? So here is our combination of openings that control the flow rate. If this is very small, we can just neglect it, and then of course these cancel. So this flow rate, this area is effectively the small opening. Right? So the whole system is controlled by the small opening. So if you work at the Center for Mathematical Sciences, you work in a naturally ventilated space like this, and up here we have a small opening at the top and lots of openings down here where there's inflow into the offices, and so the whole flow through this building is controlled by this effectively. Okay, so if I get a bit hot in my office here, I'll open my office window and I'll get a bit more fresh air, and Colin will get a bit less fresh air, but the whole flow through the building will be the same. So it's a very robust design, and that's why it looks like this. And if you work out what the height of this this cool lower layer as a function of the total height of the building, it satisfies this equation with a constant here, which I've left off, but includes the entrainment constant of the plume. So what you can see here is, of course, that as I make the area here larger, the height of that zone increases. But of course, there's a singularity here. If you try and get it right near the ceiling, this becomes close to zero, and so you need a huge amount of opening. So what you do is you make H unnaturally high, and so you build something on the top to give you an extra H, which is why that other building has tall chimneys. This is just how a chimney works. Right. And the other interesting thing about this equation is that it doesn't have anything to do with the heat flux. And that's because on purely dimensional grounds, this is a steady result, and the heat flux is the only thing in the problem which has time in its units. So it can't appear in a result that just deals with steady things. There's nothing else to balance it. So it tells you that this height is independent of the heat flux in this building. Right? So if you make it for a certain level of occupancy and you double the level of occupancy, the answer is the same. So that's why it's a very robust thing. Okay, so that was stack-driven. What about wind-driven? And this is some recent work that Megan has been doing, and Megan is sitting just there. I'm going to show you some examples of cross-ventilation. So she has an experiment set up where you have flow coming in on the left and going out through the right. And what I'm showing you here is the ventilation of this space through these two windows when the temperature difference here is zero. Okay, and what you saw from this, if you were observant, but I'll go back anyway, is that the flow comes in, as you can see. Initially there's some variation in the color, but after a while the whole thing mixes up and the dye, the tracer dilutes, just removing the concentration of dye in this way. So this is obviously well represented by a well-mixed model. So here is the dye concentration initially. Here is the bit when it comes through the window to start with, but you can see later on effectively everything's pretty well mixed, and the concentration on average decreases exponentially, and you can calculate how that works very straightforwardly. So that's a very straightforward situation. Okay. So what happens? Oh, okay. So that's cross ventilation with no buoyancy. Now the thing is that that's very rare. It's very rare to have a situation where you have a window on one side and a window on the other side, and certainly with no buoyancy. What's normally the case is that when you open up windows, you only have them on one side of the facade. And in fact, this is, as I said earlier, we know how to make new buildings work well. The real challenge is how to fix old buildings that don't work well. And the likeliest thing you'll do is just open some of the facade up, and it's likely that they'll only have access to part of the space. So there's a lot of interest in what happens if we have just single-sided, so just say a window or two windows open here and everything else closed, and how does that work? So I'm going to show you the two window case just to show you the kind of things that matter. So here is so these are wind tunnel measurements. So this is a situation where there are two windows open on the facade. The wind blows in this direction. So the yellow ones, which are yellow dots here, are close together, and the red ones are further apart. And this is the flow rate as a function of the angle of incidence of the oncoming wind. So 0 is when it's normal to the front face, and you get a flow rate here, and so forth. And as you tilt the building around, you get an increase in the flow rate, and then a reduction, and then another increase here when you get further around, and eventually when you're at 180 degrees, the wind is coming from over here. Okay, and what you can do, what we did actually, is to measure the pressures at these places and plot the mean pressure difference here as a function of this wind angle, and also the unsteady pressure difference is the standard deviation, because this is in a wind tunnel with a turbulent flow. And what you can see here is that first of all, this follows quite well the mean pressure difference and the sort of flow rate. So you have this peak up here, and then a reduction, and then we get a pressure difference of the other sign, but we still get a flow in here. Okay, and it's larger when they're further apart than it is when they're closer together. But all of the time, you get a contribution, a pressure difference associated with the standard deviation of the system. And in particular, if you go round to the lee, or in fact if you're at the front face, like here, or at the lee, then you find the mean pressure difference is actually 0. So any ventilation must be driven by the fluctuations. And you can see that there are fluctuations here and at the lee, which actually provide this additional driving. So in fact, the flow rate behaves something like this: some fraction of the mean pressure difference and some contribution from the standard deviation. What we did was to compare arrange this building either as a two-story isolated building or a four-story isolated building, and then we looked at what happens if we put buildings around it, because the question is, how does that shelter it? And what you can do, as you can see here, is you can actually characterize this quite nicely. So you can find values for the coefficient of the mean pressure difference and also the fluctuations. So the contribution of the fluctuations is always about the same, but the mean pressure difference varies a lot depending on whether the building is sheltered or not. And that's about as good as you can do with this kind of thing. But the flows are really quite interesting, and we look at the one at the. So now we're looking at the case where this is completely in the lee, and the wind is coming from the front. Coming from the front. Thank you. And you can see here that actually the ventilation flow is really just purely driven by the unsteady component of the pressure field. You get pumping, so outflow here for a while, and then inflow, and then outflow, and so on. And that's associated, obviously, with the vortex shedding around the building. And I think modeling that is a really major challenge, actually. Okay. So that was single-sided wind-driven flow. What about single-sided stack-driven flow with temperature variations? There's been some studies looking at the impacts of different sorts of windows. And what's typically done is you heat up a space like this. You put one kind of window in here. You measure the decay rate of a tracer, in this case carbon dioxide, because it's a very passive tracer. And then you measure the mass flow rate as a function of the openable area. And you get, obviously, an increase in ventilation the more you open the window, no surprise. But different shapes give you different levels, and in fact the variation can be significant depending on the different kind of window geometry. And because we use these a lot in the UK, I thought we'd just look at this one a little more. These windows go back to the period of Queen Anne. For those of you who've seen The Favourite, it's hard to imagine that people were designing windows in those days. But anyway, and there's some suggestion that they were actually, obviously done something wrong here, 1670, possibly invented by Robert Hooke. So you can build a model of this window. And I'm just going to show you what happens if you imagine that everything stays well mixed in here. Okay, so it's at some temperature which is bigger than the external temperature that's warm inside, and so forth. And typical temperatures are such that the flow is Buoyancy, so if it's cold inside, it just goes the other way. Right. And what you say is the flow inside here is slow, except near the openings, and so the pressure is hydrostatic. So you can simply draw the change in pressure, just the weight of the fluid. And the weight of the fluid inside is less than outside because it's warmer, so the pressure gradient is less. So there's some point at where the pressures are equal, the so-called neutral level. And so outside, at the bottom, the pressure is higher, and so there's inflow. And inside, the pressure is higher, so there's outflow. At the top, sorry, the inside pressure is higher, so there's outflow. And if you imagine that it's some sort of Bernoulli type thing, you can calculate the flow. I'm not going to do that. If you imagine that you have a normal sash window and you keep the top closed, so this is the glass bit, the blue bit, and just open the bottom bit, then obviously you must have equal and opposite inflow and outflow, and that means that this neutral level sits in the middle, and you can calculate what's happening. And then you can ask the question, if I open the top panel, what's the minimum I have to open it so that there's only inflow here and no outflow? And that condition is that this distance just equals the opening size. And if you open the window totally to the maximum extent, so this is half the actual total height here, then the answer is about a sixth. So you just need a small opening at the top. It's about half of the size of this bottom opening. And then the flow in here is all inwards. And why does that matter? Well, it matters for two reasons. I think one is that these flows can be quite complicated anyway, and perhaps I won't do that bit. And in particular, the kind of model that I was telling you about works well as long as there's only inflow here. So in this case, this is just the same as the displacement plume flow I showed you before. Imagine that you have a heat source here. Then, just as before, you have a heat flux in here and the same heat flux out there. These must balance. And since you know this, because this flow rate must equal that flow rate, you can solve this problem. On the other hand, if you make this too small so that this interface sits below the level of this opening, then there'll be outflow here, and we no longer know how you'd partition the outgoing flux. And what we expect to happen then is, because in these situations you get the so-called filling box thing, we'll imagine much more complicated stratification here, and it's a much more difficult problem. So it tells you that the performance of these windows not only depend on how much you open them, it depends on the height of the sill, right? So if it's low down to near the floor, then it's and this region is above that, which is determined by this flow rate, then you get one behavior. If the other hand, the sill is up here somewhere, then it behaves differently. So even something as simple as this can be relatively complicated. Okay, and now I want to just combine the wind and the temperature together and show you some more of Megan's experiments. So now, instead of having, so now this is a warm room, just heated up to some value, and then we define a Froude number, which is the flow speed divided by the characteristic buoyancy speed based on the height of the window and the buoyancy of the temperature difference here. Beta here would be 1 over the absolute temperature. Yes? That's a good question. All right. So in the case when delta T was 0, we saw it was well mixed. Okay. So no, don't steal my thunder. Okay. Right. So now here we have a strong wind. So the Froude number is close to 2. So it means the wind speed is twice the buoyancy speed, or 1.75. Okay. And now you see the flow is completely different from the previous case when there was no density difference. I hope you can all find your favorite instability here. You can see that over time that actually changes. There's a lot of turbulence and mixing, initially kind of associated with the convective overturning of this region. And later on, now you can see actually a sort of scouring flow across here, impacting this wall and some overturning here. So we have lots of applications of stratified mixing in this situation, even though the buoyancy effects are relatively small. So the wind is still dominant in this case. But it changes the flow pattern completely. So even small amounts of stratification change the behavior. Okay. And you can see eventually this sort of erodes this upper region, very much like kind of classical mixing experiments across interfaces. On the other hand, if you make the buoyancy and the wind speed essentially the same, now you still get inflow on the windward side and outflow on the outward side, but there's actually a little evidence of some outflow happening just on the windward side here, just when they're matched, but that looks rather like the strong wind case. Okay, and again, we have a process initially of a convective mixing of this cold air coming in, and then later an erosion of this. And finally, if we make the buoyancy very strong, now we get outflow through the windward window and outflow through the leeward window, and very vigorous mixing again, convective mixing, internal waves, all sorts of wonderful things happen in here. So just adding buoyancy in this very simple way changes the flow by an order completely. And in fact, the consequences of this are quite interesting. So first of all, you can make a reasonable estimate of what happens if, at least for the initial phase, if you imagine that all of this region below the window here is well mixed, which as we saw was an approximation to the truth, but it gives a reasonable estimate for this decay of the temperature. But the later stages, once you're scouring this interface, then we see a completely different behavior, and this is really an erosion process. And if you want to know more about that, please ask Megan. Okay. But the other curious thing about this, I think, is imagine that the wind is really strong, and you add some buoyancy to the system. Then essentially what happens is that when the wind is very strong, essentially it flows through the window in this direction. When there's some buoyancy, it retards the flow at the top part of the window and enhances the flow at the bottom part. And that change in area is reflected by a change in the flow rate compared to the wind driven case only, which is given by this formula. But the interesting thing about it is this is where wind and buoyancy are equal, and here when the wind is 3 times as strong, and the change in the flow rate is only 5%. Okay, so the impact of the buoyancy, actually it's negative because you're increasing buoyancy this way. When you put buoyancy in, the flow is reduced, but the effect is relatively small. So so in the case when the wind dominates, you can probably just imagine that the buoyancy is really irrelevant here in this situation, because the error would be 5%. On the other hand, if the buoyancy dominates, so initially you've got through number 0, you've got an exchange flow through both openings, and then as you increase the effect of the wind, you force all inflow here. Then through the same argument, you make a big difference now to the flow through this window. It's almost 0 here, and it's a lot here. So this flow rate now changes by 50%. Okay, so if you've got a buoyancy-driven flow and you add a small amount of wind, you change that hugely. Right? So qualitatively different depending on which of the two forces is dominating. Okay. All right, so what I want to do for the rest of this talk is really just to sort of build on what I've just been talking about, the physics of these buildings, and just say a little bit about the sort of magic project that we're working on. Quite a lot of this you will resonate with what Martin and Catherine said today, so I'm not going to spend too much time on it. But I wanted to show you those kind of simplified models of buildings, because as you heard, people want to make a decision about, is it a good idea to use natural ventilation? Can we make a rough and ready calculation? How should we design various openings? These kind of models are very useful for that, and you can do them, and they're moderately accurate. Okay. If you want to do more than that and couple them accurately with the external flow, then you can see, for example, that from the wind-driven case, as I showed you, you need to know the pressure on the building facade. And in fact, you need to know the difference in pressure from one place to the other. Both highly resolved in space and time. So this is hard. Okay, you need to know for the buoyancy case what the external conditions are: temperature, solar radiation, and that's complicated, as you heard before, by radiation from buildings and by shading. I haven't mentioned much about this, but if you're bringing air from outside in, you want to know what the external pollutants are that you're bringing in. So you need to know something about that. And of course, you need to know what the internal conditions are, what the temperature is inside, what the internal pollutants are, and so on. So these are the kinds of things you need if you're really going to couple the buildings with the external flow. So as a result of that, we're in the middle of this magic project. It's a 5-year project, and we're about halfway through. And it has a whole bunch of components which I won't go into in too much detail, but essentially we focused around a field study, and I'm going to describe the results of the field study. And what feeds into this is an LES code called fluidity, water models that Megan and I just showed you, some wind tunnel work. We also do energy analysis, and then some other aspects of reduced order models and data assimilation. And this is a Gaussian plume model for comparison. But we're all focusing around this field study. I'm going to tell you just a little bit about that. No, I'm not. I'm going to tell you this first. Okay. So as I said, so fluidity is the fluid mechanics of this is fluidity, a large eddy simulation model. It has a fully adaptive mesh, and we put in an explicit representation of urban form. There was some discussion this morning about whether you can find out generic answers to cities. I think they're just too complicated. I think you need to do the geometry specifically, and I'll show you one example of that. We have a wind tunnel study of our test site. We do water flume modeling of the indoor-outdoor exchange. I've shown you those, and monitoring of indoor and outdoor conditions, and I hope I'll answer your question about what happens inside a real building. Okay, so this is what we did in the summer of 2017. Our tests, this is London, it's the Thames, we're south of the Thames. And the red area is our test site. It's about 300 meters in radius. And this yellow bit here is actually the test building. And we have a test room located here. It's an unusual geometry because the roads are radial. So it's not like an American city. And there's a sort of roundabout area here. And this road here is called London Road. It's full of traffic. And at the back of this yellow building is a clean courtyard. And so we're very interested in understanding what happens locally and also in terms of the region around it. So this is a blow-up of the test site. So here is this roundabout. Here is London Road. And our test building is here, and we actually have, ignore that, we have an office up in here, where we're measuring here is the courtyard around here. This is part of the London South Bank University, and they're building, like many UK universities which charge exorbitant fees to students, they have lots of money, and they're building buildings around this site faster than you can imagine. So it's changing every 6 months or so, but we still have this courtyard here. Okay, and we have a test room which has 2 windows on the London Road side, and it's a single office. I'll show you a plan view, and a single window at the back, so it does allow cross ventilation. We can open both windows, or if we keep one or other facade closed, we can have single-sided ventilation. Another view of London Road, a bit like a street canyon, but irregular with holes in it, and you can see it has some vegetation, some trees. Our building is sort of just tucked in here, there, and lots of traffic. Okay, and what we did was deploy sensors both externally and internally. So this is our test site here, and we have sensors in London Road and at these green locations. And within this space, which was occupied by a startup, so they had 6 to 7 people crammed into this tiny office, with 2 windows on the London Road side and 1 window in the courtyard side, and in fact a skylight as well, which I haven't mentioned. Shiwei here built so sensors which essentially measure NO2, CO2, CO, temperature, and relative humidity. And I'll show you some of the results from those measurements. In fact, this last summer we also deployed, did another test study in Cambridge to look at the effects of green spaces, but we haven't analysed the results, but that just shows you a close-up of how we monitor, put things on lampposts like this to measure the external positions and so forth. Okay, conditions. Okay, so first of all, let's have a look at the NO2 on London Road. So these plots are such that when the wind blows from, say, the southwest, we have a point on this direction, and the color represents the NO2 along that trajectory at any time. And so you can see as the wind varies, we get to different levels of NO2 as it varies direction. And and these 2 monitors are on 2 sides of the same road, the side of London Road. This side is on the side, the wind blows from this direction, London Road looks like this. So this is on the, I don't know how you call it, the leeward or the windward side, but it's the one where the wind blows over the building and then over the road, and this is the other side of the road. And you can see immediately that there's a huge difference when the prevailing wind, which is the southwest, here we get high concentrations of NO2 on one side of the road and tiny concentrations on the other side of the road. So this is a very nice example of the street canyon effect that we heard about today. And of course it tells you that you should always walk on this side of the road and not this side of the road. And that kind of information is the sort of information that one needs as you're trying to reduce your own personal exposure. And in fact, if we look around the whole region, you see huge variability in concentrations of NO2. All of this is essentially from traffic emissions. So for example, here on this sensor here, whenever the wind blows from the northwest, huge concentrations along here. That's because there's a whole series of buses come along here and stop, and they essentially contribute hugely to that. And it is the case that odd vehicles really produce huge amounts of well above the sort of baseline average. So if you have 1 dirty vehicle or 2 dirty vehicles, it makes a huge difference. Okay, so to give you an idea of the kind of indoor-outdoor exchange behavior, so outside here is the black line is the carbon monoxide measured on the roadside. This is measured about 3 meters above the ground, and the red line is what's measured inside the test room over a series of days. So you see a very clear cyclical behavior associated with rush hour, and you also see that the level outside is always bigger than the level inside. And that's slightly surprising because CO is essentially a passive tracer, and there is exchange between inside and outside. But it just goes to show that what happens at our windows is actually significantly different quantitatively, although qualitatively the same, that happens at 3 meters. So there are vertical variations in concentration of pollutants as well as horizontal variations. Okay. And you can also look what happens when you look at what happens inside. This may answer the questions about variability. So here is a day. People come to work in the morning and they breathe out CO2. This is CO2. And the CO2 level rises. About 12 or so, 12:30, a few of them go out for lunch and the CO2 levels drop. And then it gets up to about 1,000 ppm and they think it's really stuffy. So they open the window and the CO2 level drops, but not uniformly. Okay? And then they close the window again and the CO2 level rises and they all go home and it decays away. So nothing too surprising, except this variability is enormous. Huge ranges here from place to place inside the room. So not at all a homogeneous interior place. Okay, so well mixed it's not, right? And in fact, it's vertically stratified both with temperature and carbon dioxide. I'll just show you the carbon dioxide data. So this is the carbon dioxide. The blue line is measured near the ceiling at over 2 meters, and the black line is measured near the floor. You can see consistently that the highest levels are near the ceiling and not near the floor, and carbon dioxide is heavier than air. And that's because it's temperature stratified, and the temperature stratification far outweighs the carbon dioxide. The effect on temperature far outweighs the effect of carbon dioxide on density. And so you have this, what appears to be an unstable profile of carbon dioxide in the room. So where you measure it, if you're going to have a monitor to determine where you measure CO2, in most cases they're kind of about here. Okay, and actually they should be up there because that's where all the CO2 is. In fact, they should be up there because it's all up there with these guys, the cool kids at the back. Okay, and you can compare single-sided ventilation, which has this large variability, to a case when there's cross-ventilation, which is much more efficient at flushing things out and things are much more uniform. So you see variations in that form here. Okay, I should stop in a minute. So I'm not going to talk too much, but we've done wind tunnel models and we compare them with the LES simulations, and they agree well, although Catherine implies that they don't agree with the real thing. But what we do see is a transverse across here is this huge reduction in streamwise velocity when the wind comes here, because there's a very tall building here. So we have a huge wake that lasts 3 or 4 building heights downwind. So the idea that this is some kind of boundary layer with roughness is completely wrong. And as I said, they're building new tall buildings around this space as we speak. Okay, I'm not going to go through all this. Just to say that the idea eventually is to have a decision support system, which includes this the LES model, but surrounded by other things too, using reduced order modeling, in particular using data assimilation and uncertainty quantification. So many of the things that Catherine talked about, we're also very interested in and incorporating in this, and we are also using reduced order models to reduce the run times. So instead of using the full model, we take a representation based on a reduced number of basis functions and do that. And the speed up time here is enormous. To run this for an hour in real time takes 2 weeks, and to run this for an hour in real time takes about 30 seconds. Okay. And we're also trying to model things like vehicles and so on, and working closely with Transport for London and others. Okay. Okay, so the idea is that we'll end up with this suite of models with management tools and decision support tools, and based on the best science we can do for our air quality, and then using reduced order models to provide better, more rapid calculations and so on. And it's a very interdisciplinary project. So all of these departments are involved across 3 universities, and we collaborate with the Greater London Authority, Transport for London, the Department of Environment, Food and Rural Affairs, and other people to try and talk to policy people. And we have a magic circle, which consists of our inaugural partners, and we have about 30 industrial, which is loosely defined, which also includes things like local councils and so forth, and 21 university members, and anyone can join. And if you want to join our circle, you get a magic circular once a quarter, and you're invited to our magic meetings once every 6 months. This is our original set of partners. Some of the names will be familiar to you, like perhaps like Arup and Foster and Partners, and maybe Dyson and others. And we have a whole bunch of other people who join us, including Lab in Lyon. Just to say what I think the future challenges are here, I think we're going to see increasing amounts of monitoring in cities. The kind of monitors we made cost about £300 each, so they're not expensive. They're not very accurate either, but they're not expensive. So there'll be a lot of monitoring, and lots of questions about how you deal with the data. I haven't talked at all about indoor pollutants, and that's a really big and increasingly important area. We spend almost all of our time indoors, actually, 95% of our time indoors. So what happens indoors really matters. And we're very interested in trying to use these kind of approaches to mitigate your own personal exposure. As I said, you've got to walk on the right side of the road. And then, of course, in the longer term, we'd like to understand more about impacts on productivity and impacts on health and well-being. And I think it just leaves me to put up all the people who are involved in this project. It's a huge undertaking, and I thank you for your attention.
Thank you, Paul. We have time for a few questions. I have a stupid question. In the street, there are cars, but there are also people that walk around.
They do.
Are they somehow mixing the pollutant or not at all? Is the effect negligible, or especially, for example, in Asian city where there are so many people?
Yeah, I think it's not negligible. Nicola here has been doing some work on people walking in corridors, and we did some work on people walking through doorways, and they have an enormous effect. I was quite surprised, actually. On the broader scale of a street, well, obviously it depends on the scale of the street compared to the number of pedestrians, but I can imagine situations where it matters. Yes, I think so. Yes.
So that's from people breathing?
No, carbon monoxide is from cars.
So
it's correlated with rush hour. So we monitor CO2, which is essentially produced inside and not much outside, because it's 400 parts per million outside. And we monitor CO, because that's produced outside and not inside. And so by looking at the two of them, and they're both chemically stable, they act as passive tracers to help you figure out the ventilation in and out, essentially. It was higher outside. Yeah.
So how do you plan to design the sensor distribution? Do you want them on the buses, on the cars, or do you want them stable, these small ones? And can you do, like we do, ocean observing system simulation experiments? We do have virtual sensors. We see how they mark the thermodynamics and the dynamics.
Yep. Yeah, so the plan is partly to use data assimilation techniques for that, to find the most sensitive places to place stationary monitors. But I think there's a lot of scope now for mobile monitoring. Someone mentioned Google cars, but I'm sure that that kind of thing will increasingly be the case. I think thinking about how you deal with that data will be really an interesting challenge, actually, getting information out of lots of data. Yeah.
Luke has a question.
Luke?
I guess in London it gets hot in the summer, but not that much. And how would you see this being applied in places where it's really warm and humid for a long period of time in summer?
Yeah, that's a very good question, of course, and I wouldn't suggest that this is necessarily a solution for places like Singapore or Hong Kong. I think the tropics is really tough, actually, because not only is it hot and humid all the time, it doesn't even cool down at night. So there are many strategies you can use if you have diurnal variation. So, for example, we worked on a building in Malta, which was a naturally ventilated brewery, and it was critical that you keep the brewing hall at 23 degrees, and the external temperature went from like 18 at night to 40 in the day. But by using night ventilation to cool the external and had a double skin, you can actually make this work, with thermal mass. So there are ways of using these things that are much, more sophisticated than the kind of thing I was talking about, if you understand the ventilation flows. But hot, humid climates, that's really tough. Yeah, don't build big cities there. It's really a bad idea.
Okay.
So you showed the CO2 concentration in the room, which somehow was inverted as compared to what you would expect from the density.
Yeah.
So can this be seen as a double diffusion
Yeah, I think it probably
problem
can.
with temperature on the one hand
Yeah.
and CO2 concentration on the other hand?
Absolutely. Yeah. I mean, it's just the diffusivities are almost the same. That's the problem, right? So CO2 and temperature, they're essentially, the Prandtl number is 0.7. So it's, so it's essentially, they're almost the same, I think. So that's the problem. So it's weakly double diffusible. So it's not identical. Yeah, it's about 1. Yeah, that's the problem. Yeah, but I think in practical terms you won't see it. I don't think. Yeah, sorry.
You mentioned a lot of things about improving the buildings that are right now
Yes.
non-efficient. So they are usually very squared, or is there something still to find in the geometry of rooms or of roof, or the top part of the room only, or are there things in the geometry side to optimize those ventilation?
Well, yes, there are clearly things you could do. So, for example, you could, if you were going to ventilate this room, I would open those windows up the top, and I'd have something down here that brought some cold air in, right? And that would be really much better than the current arrangement, certainly in the summer. In the winter not, but in the summer. Okay, and so something like that you could do. But if you were going to refurbish, say, this room, you wouldn't start changing the roof, right? It's just too expensive. So I think what you kind of have to work within your limitations, really, if you think about that. So the refurbishment problem, which I think is a really important practical problem, actually, I think you're working in a very constrained space, actually. And that's why we've sort of concentrated on, well, what happens if you just open the facade? Because that's the simplest thing you can do. What do you get for that?
So thank you, Paul, for this very nice talk. I think we should